In this section, we start going deeper into permutation. Let's try to analyze the various types of prominent questions that can come from this section. The first question that we analyze is questions of the type where you are asked to arrange n things, and out of these n things, A items are identical and another B items are identical. This can be done as n factorial divided by A factorial into B factorial. Let's take an example to understand this better. Say you are asked to arrange the letters in A, B, C, 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 D, D in unique ways. This can be done in 7 factorial divided by 2 factorial into 3 factorial ways. Why? Because the total number of letters given over here are 7. That's 1, 2, 3, 4, 5, 6, 7. That's your numerator. And 3 are of one type and 2 are of one type. That's why in your denominator you have 2 factorial into 3 factorial. Now let's take a simple example to understand this better. Say you are given 3 letters A, B, C. What are all the ways in which you can arrange these letters? You have A, B, C. You can do it as A, C, B. You can do it as B, A, C, B, C, A, and C, A, B and C, B, A. Right? So these are the 6 ways in which you can arrange these 3 letters in 3 places, and that is nothing but 3 factorial. Now over here you can see A, B and C all are different. That's why it's 3 factorial. Even in this case, if all the 7 letters were unique, that's they are different, the answer would have been 7 factorial. What is the case if the 3 letters given are A and C? Over here, the different ways in which you can arrange these 3 letters is AAC, ACA and CAA. There is no other way in which you can arrange these letters, right? And this over here is equal to 3 factorial divided by 2 factorial, because 2 are of one type. And 3 factorial by 2 factorial gives you 3, and that is these 3 arrangements, 1, 2 and 3. Alright, so let's quickly recap. If you have n items and of these n items, A items are of one type and B items are of one type, then the number of arrangements possible is n factorial divided by A factorial into B factorial. Alright, let's move on. We'll see one more type of question in this video. Let me make some space over here. Alright, now when repetition is allowed, how many ways can you arrange 5 rings in 4 fingers? And remember over here, the rings are different, 5 different rings. Imagine that they are not identical, they look different, 4 different types of rings, and obviously the 5 fingers are also different. So you are arranging different things into different things. That's this type of question. Now if you want to arrange 4 rings on 5 fingers, each ring can go in any one of the 5 fingers, that is the 5 positions, right? Therefore the first ring can be arranged in 5 ways, the second one in 5 ways, the third one in 5 ways, and the fourth one in 5 ways. Therefore the first and second and third and fourth ring can be arranged in 5 into 5 into 5 into 5 ways, which is 5 to the power 4. So remember, the second type of question that we have discussed in this video is cases where you are given different items and you are asked to put them in different positions. In this example, we were asked to put 4 different rings on 5 fingers, and obviously the 5 fingers are different. Let's do this question. 10 different letters are to be dropped in 4 different letter boxes. In how many ways can this be done? Alright, pause the video, give it a try, and then we'll do it together. Alright, we are back. I hope you have given it a try. Let's do it together. You have 4 boxes, right? And let's take any one of the 10 different letters. So let this be letter 1. Now this letter can be posted in any one of the 4 different letter boxes, right? So this one can be posted in 4 ways. Similarly, the next letter also can be posted in 4 ways, right? Because it can be placed in any one of these 4 letter boxes. Therefore, when you take all the 10 different letter, it can be posted in 4 into 4 etc 10 times ways. That's equal to 4 to the power 10, which is your answer, which is option B. Now, it's easy to get confused in this type of questions between 4 to the power 10 and 10 to the power 4. So the way out is, do not by heart it. Don't try to memorize this type of questions. Rather, take any one item and see in how many ways it can be arranged. And in that manner, you will easily be able to arrive at the correct answer. Let's do this question. How many words can be formed using the letters of the word arrangements? Pause the video, give it a try, and then let's do it together. Alright, we are back. I hope you have given it a try. Let's do it together. So the word given over here is arrangements. You can see that this is a 12 letter word. Therefore, the numerator is 12 factorial. Now, you can see that R is repeating 2 times. Therefore, you have to divide it with 2 factorial. Similarly, A is repeating 2 times. You can see that N is repeating 2 times. And you can see that E is repeating 2 times. Therefore, your answer is 12 factorial divided by 2 factorial into 2 factorial into 2 factorial into 2 factorial. Let's do this question. All the words that can be formed using the letters of the word skills are arranged alphabetically. Alright. Find the rank of the word LSKILS. Alright. So we know that using the letters in skills, that's 1, 2, 3, 4, 5, 6. 6 letters. You can form 6 factorial divided by 2 factorial into 2 factorial words, right? Because L is repeating 2 times and S is repeating 2 times. Now, all these words that are formed, and all of them need not have a meaning, are formed and they are sorted and listed alphabetically. Now, one of these words will be this one which is given. We need to find the rank of this word. Pause the video, give it a try, and then let's do it together. Alright, we are back. I hope you have given it a try. Let's do it together. The first step is write the letters in skills alphabetically. That would be IKLLSS. Now, the words that are formed in the beginning will be starting with I, right? Because we are arranging them alphabetically. Now, how many words will be formed that start with I? That would be arranging the remaining letters, right? So that's 1, 2, 3, 4, 5. 5 letters, of which 2 are of one type and 2 are of one type. Therefore, starting with I, we can form 5 factorial divided by 2 factorial into 2 factorial words. Similarly, the next set of words will start with K, right? After the words that start with I are over. Now, how many words can you form that start with I? Again, it's 5 letters, of which 2 are of one type and 2 are of one type. So you can form 5 factorial by 2 factorial into 2 factorial words that start with K. Now, after that, we go to L, right? And over here, L is what we want in the given word. So after L, what would be the next letter that would come? It would be I, right? So how many words will be formed with Li? That would be 4 factorial divided by 2 factorial, right? Why is that so? Because once Li are arranged, we are left with 4 more letters, right? Let me make some space over here. So L and I are consumed, right? So L is gone, I is gone. We are left with 1, 2, 3, 4. 4 letters, of which 2 are of one type. Therefore, words that start with Li will be 4 factorial by 2 factorial. And these words will be before this word over here, right? Because after L, you have S over here. Alright, similarly, after Li, what will come? That's so after I, again alphabetically K comes, right? So we will have Lk. How many words will be there that start with Lk? That would be again 4 factorial divided by 2 factorial, right? Why is that so? L is consumed and K is consumed. We are left with 4 letters, 2 are of one type. So that's 4 factorial by 2 factorial. Alright, now we have finished the words that start with Li. We have finished the words that start with LK. Now, because we have two L's, the next set of words will be those that start with LL. And words that start with LL will be of 4 factorial by 2 factorial count, right? Because L and L is consumed, we are left with these 4 letters and 2 are of one type. Therefore, you can form 4 factorial by 2 factorial words that start with LL. Similarly, after that, what will come? S will come, right? We have finished LI, LK and LL. After that, it will be LS, and that's what we want over here. So we keep that as it is. After that, what will come after LS? What will come? So L is consumed and S is consumed. Again, we check alphabetically. It would be starting with I, right? So how many words can be formed with LSI? That would be 3 factorial, right? Why is that so? Let me make some space over here. What are the letters that are consumed? It is L, S and I. So I have consumed L, I have consumed S and I have consumed I. I'm left with 1, 2, 3 letters and there's no repetition. So 3 factorial words can be formed with LSI, starting with LSI. Now after that, what happens? We have LS and we have consumed I, right? In alphabetical order, you will get K after that, right? But that is what we want in the question. So we keep K over here and we move on. Again, we check alphabetically. What would come? I will come, right? Now that's what we want in the question. So let's keep I over here and move forward. Now again, we check alphabetically. Let me make some space, some clarity over here. So what are the words, letters consumed? L is consumed, S is consumed, K is consumed and I is consumed in this part, right? We are just left with L and S, and if you arrange them alphabetically, L will come before S, right? So the next letter will be L and the next one would be S, and this is the same word that we are finding the rank of. So this will count for 1. All right, now let's keep these aside. We have seen that before this word over here, which is the one that we are trying to rank, there will be 30 words that start with I, 30 words that start with K, 12 words that start with LI, 12 words that start with LK, 12 words that start with LL, and 6 words that start with LSI. And the next one after these many are over will be the one that we are finding the rank of. Therefore, the rank of this given word is equal to 30 plus 30 plus 12 plus 12 plus 12 plus 6 plus 1, which is nothing but the sum of these numbers over here, and that is equal to 103, which is your answer. Let's continue in our way going deeper into permutation. So far we have discussed these 2 types of questions where we had n things of which A are of one type and B are of one type. We have discussed this, and we have also discussed the case where different items were to be placed in different positions, right? For example, 4 different rings were to be worn in 5 fingers. All right. Now, the next type of question that we encounter is circular permutation. Now, if you have n items and you need to arrange them around a circle, this can be done in n minus 1 factorial ways. Remember, in the case where you have n items and you want to arrange them in a linear manner, if all the n items are unique, this can be done in n factorial ways. But if the n items which are unique have to be placed around a circle, this can be done in n minus 1 factorial ways. For example, say you have 3 people R, G and B. This could be Rahul, Gobu and Babu. So these are 3 friends. All right. Now you need to arrange them around a circle. They can be arranged in these 2 manners, right? These are the only 2 ways in which you can arrange these 3 people around a circle. What would be another way you could think of? If you think that having G over here, R over here and B over here is another arrangement, that would be not true, right? Why? Because this arrangement over here and this one over here, they are both the same, right? Just it's a rotation. If you rotate this a little bit over in this direction, R will come over here, B will be over here and G will be over here, which is the same as this one. So there are only 2 ways in which these 3 friends can be arranged around a circle. All right, and we get this, that is 2. This is 1, this is 2. We get this 2 by taking 3 minus 1 factorial, which is equal to 2. Now, this also can be thought of in a different manner. The question is about fixing one position, and then for the remaining n minus 1 items, it's equal to linear arrangement. So for example, I fix R over here, then I am left with 2 items, right, or 2 people, and 2 people in 2 positions can be arranged in 2 factorial ways when it is linear arrangement. So we have seen circular arrangement and we have thought about it in 2 ways. One way is that you can arrange items around a circle in n minus 1 factorial way, or you can think of it as fixing the position of any one of the given items and the remaining items have to be arranged in a linear manner. Either way, you get the answer as n minus 1 factorial. Alright, let's see a special case in the case of circular permutation. If these 3 items are not people but they are red, green and blue pearls. Alright, now in this type of a case where you cannot differentiate between clockwise and anti-clockwise direction, the number of ways of arranging them around a circle is n minus 1 factorial by 2. Now over here you have 3 colored beads, for example, or pearls. In this case, the bodies are symmetrical from top to bottom, right? Therefore this arrangement and this arrangement is not different, but it is the same, right? If you look from the top, you will see it in this manner. The same arrangement, if you look at it from the bottom, you will see it like this. Therefore, in the case where the bodies which are arranged around the circle are symmetrical from top to bottom, or if you cannot differentiate between clockwise and anti-clockwise direction, these two are one and the same, in those cases you have to find n minus 1 factorial divided by 2. Let's see this in the manner of a diagram. Over here we have the 2 ways in which we could have arranged 3 people around a circle, but instead of people we have kept colored beads. So this one is blue, this is yellow and this says orange. Now if you look at it from the top, you will see this view, right? The same thing without doing any change. If you look at this arrangement from the bottom, it will become this one over here, right? Therefore these two are one and the same, and that's why over here the possible arrangements is 3 minus 1 factorial divided by 2, which is 2 by 2, which is equal to 1. So if you are given 3 colored beads, the number of arrangements around a circle or the number of ways in which you can make necklaces out of them is only 1. Let's do this question. How many necklaces can be formed with 5 pearls of different colors? Now, if you want to form a necklace that's arranging the pearls in a circular manner, right? Alright, pause the video, give it a try, and then let's do it together. Alright, I hope you have given it a try. Let's do it together. This is a question of circular permutation, right? And the pearls are symmetrical from top to bottom. Therefore, we have to divide n minus 1 factorial by 2. And over here n is given as 5. Therefore, the answer is 5 minus 1 factorial divided by 2, which is 4 factorial by 2. 4 factorial is equal to 24. Therefore, this is equal to 24 divided by 2, which is equal to 12. Let's do this question. In how many ways can you arrange 5 people around a circular table such that A and B always sit together? Alright, pause the video, give it a try, and then let's do it together. Alright, we're back. I hope you have given it a try. So the 5 people are A, B, C, D and E. And it is given that A and B are always together. So we have 4 units over here, right? This is 1 unit, this is the second one, third, and this is the 4th unit. So we have 4 units. Now if we have to arrange 4 units around a circle, that can be done in n minus 1 factorial way or 4 minus 1 factorial way, which is equal to 3 factorial, right? And remember, over here we have people and these are not symmetrical top to bottom, right? Therefore we don't need to divided by 2. Alright, now it's also given that in each of these 3 factorial ways, a and b are together, right? And among these a and b, they can be arranged in 2 factorial ways, right? In each of the 3 factorial ways, there can be 2 factorial arrangements between a and b. Therefore, the answer to the question is 3 factorial into 2 factorial, which is equal to 6 into 2, which is equal to 12. Let's continue in analyzing different types of questions that can come from permutation. So far we have discussed these 3 types. We have seen the case where n items are given and a are of one type and b are of one type, and we had to make arrangements out of these, right? This can be done in n factorial by a factorial into b factorial ways. We have seen the case where different items had to be put in different positions. For example, 4 different rings had to be placed on 5 fingers. This can be done in 5 to the power 4 ways. Alright, now the third type of question that we discussed is circular permutation. If you have to arrange n items around a circle, it can be done in n-1 factorial ways, and if the items that we are arranging around the circle are symmetrical top to bottom, this can be done in n-1 factorial by 2 ways. Alright, the next type that we discuss over here is restricted permutation. In restricted permutation, you might be given some conditions and you need to form arrangements such that the given conditions are adhered to. For example, say these are 4 doors of adjacent rooms. Now, we need to paint these 4 doors using the colors in WebGR. So in WebGR, we have 1, 2, 3, 4, 5, 6, 7. We have 7 colors at our disposal. And let's do a few questions in this context. Say no condition is given and repetition of colors is not allowed. That is, once you paint a door in a particular color, you cannot paint the remaining doors in that color. Other than that, there is no condition. So this can be done in 7p4 ways, right? Which is nothing but the number of ways in which you can select 4 items from 7 items and arrange them among themselves, right? This can be also thought of as, say this is door 1, door 2, door 3, door 4. The first door can be painted in 7 ways. The second one can be painted in 6 ways, except the color which is already used over here, because repetition is not allowed. The third door can be painted in 5 ways and the fourth door can be painted in 4 ways. So these 4 doors can be painted in 7 into 6 into 5 into 4 ways, which is the same as 7p4. This can also be thought of as 7c4 into 4 factorial. 7c4 is the number of ways in which you can select 4 items from 7 items, and after you have selected 4 items, you can arrange them among themselves in 4 factorial ways. All of these are one and the same. That is this one, and what we get over here. All these 3 are one and the same. Alright, now let's move on. Say repetition is allowed. That is, you have to color these 4 doors, and even if you use a color, you are still allowed to use the same color in the next door. Now, this can be solved in 7 into 7 into 7 into 7 ways, right? Because the first door can be painted in 7 ways, any one of these 7 colors. The second door also can be painted in 7 ways, and that's the same case with the third and the fourth door. So each of these doors together can be painted in 7 into 7 into 7 into 7, which is equal to 7 to the power 4. Alright. Now, the next question is, say repetition is allowed, but adjacent doors should not be of the same color. That is, you can use the same color again, but if you have painted one door in a particular color, the door that is adjacent to it should not be painted in that color. Alright, so the first door, let me number these doors as 1, 2, 3 and 4. The first door over here can be painted in 7 ways, right? Because you can use any color from WebGR to paint this door. Now the second door can be only painted in 6 ways, right? Because you cannot use the color that you already used in the first door. Now what about the third door? The third door also can be painted in 6 ways, because the only color that it should not be used for painting the third door is the color used to paint the second door. Therefore, the third door also can be painted in 6 ways, and the fourth door also can be painted in 6 ways. The only color which you cannot use to paint the fourth door is the color used to paint the third door. Therefore, when repetition is allowed but adjacent doors should not have the same color, you can do this in 7 into 6 into 6 into 6 ways. Alright, let's keep that aside. Now, say you need to color these doors such that color V and color I is always included. That's from VibGeo, right? You have these 7 colors, and out of this, color V and color I is always included. Now, let's first make the selection. So over here, if repetition is not allowed, okay, repetition not allowed, you need 2 more colors, right? So you have 5 colors over here except V and I, and out of this 5 you need to do a selection of 2 colors. So let's make the selection. That can be done in 5C2 ways, which is selecting 2 items out of 5. Alright, now along with V and I and these 2 items which we have selected, we have 4 colors. Now we have 4 doors to paint. So 4 colors in 4 places can be arranged in 4 factorial ways, right? We have already seen that n items in n places can be arranged in n factorial ways. Therefore, making a selection of 2 more colors and arranging the 4 colors can be done in 5C2 into 4 factorial ways, right? And it's over here you have multiplication because it's and. It's making the selection and doing the arrangement. Over here, the selection is only of 2 colors and the arrangement is for 4 colors. And selection and arrangement can be done in 5C2 into 4 factorial ways, which is your answer when V and I is always to be included when you want to paint these 4 doors. What is 5C2? It's 5 into 4 by 2. What is 4 factorial? It's 4 into 3 into 2 into 1, which is equal to 24. Therefore, 5C2 into 4 factorial is equal to 24 into 10, which is equal to 240, which is your answer when V and I is always to be included and repetition is not allowed. Alright, let's move on. Say the case is that V and I should never be included. Alright, so V should not be included, I should not be included. You are left with 5 colors. Now, if repetition is not allowed, right, you need to select 4 colors to paint the 4 doors, and you need to do the selection from among 5 colors because V and I should never be included. Therefore, let's make the selection. It can be done in 5C4 ways, which is the number of ways of selecting 4 colors from 5 colors, right? Now, after you have done the selection, let's do the arrangements. You have 4 colors which you have selected over here, and you have 4 doors on which you need to apply the colors. So this can be done in 4 factorial ways, right? Therefore, the selection and the arrangement can be done in 5C4 into 4 factorial ways, which is your answer when V and I is not included. And you can note that this over here is the same as 5P4, right? And remember, 5P4 is the number of arrangements you can do by selecting 4 items from 5 items, and this is what we are doing over here when the case is such that V and I is not included. Now, let's summarize what we learned in this video. When you have some condition to apply when you form the arrangements, which is restricted permutation, first make the selection applying the restriction and then do the arrangement. So split it into 2, do the selection and then do the arrangement. If you follow this, you will be easily able to solve questions where you have to apply restricted permutation. Let's do this question. The CEO, CTO and COO of a company along with 5 more people are set to address a gathering of MBA aspirants. The CEO has to speak before the CTO and the CTO has to speak before the COO. In how many ways can the organizers arrange the sequence of speaking by the 8 speakers? Alright, pause the video, give it a try, and then let's do it together. Alright, we are back. I hope you have given it a try. Let's do it together now. We have 8 people, right? That's CEO, CTO and CEO. They make 3 people, and it's mentioned that there are 5 more speakers. All right. Now, when we make a sequence of speakers, there would be 8 positions. Let me mark the 8 positions over here like this. And it is mentioned that the CEO has to speak before the CTO and the CTO has to speak before the COO. All right. Now, the first step over here is let's make 3 places for the CEO, CTO and COO, right? So let's choose 3 places out of the 8 available places. This can be done in 8C3 ways, which is selecting 3 out of 8, right? Out of these 8 places, we choose 3. Now, if we choose any 3, right? Let me, for example, choose this position, this one and this one. Now, among these 3 positions, in how many ways can we arrange the CEO, CTO and COO? Let's think of that. The number of arrangements in these 3 places for the CEO, CTO and COO. You can do that only in one way, right? Say for example, these are the 3 positions that we have chosen. Now, over here you have to keep the CEO, over here you have to keep the CTO and over here you have to keep the COO, right? Because it's mentioned that the CEO has to speak before the CTO and the CTO has to speak before the COO. Therefore, after choosing 3 places, among these 3 places, there is only one arrangement which satisfies the given criteria. Alright, now over here we have 5 more places left, right? And there is no criteria or no restriction in the sequence in which these 5 people can be arranged to speak. Therefore, these 5 people can be arranged in 5 factorial ways, right? That's 5 people in 5 places, and that can be done in 5 factorial ways. Therefore, you can arrange these 8 people in 8C3 into 5 factorial ways. Why is that so? You have to do the selection of 3 places for the CEO, CTO and COO, and you have to arrange them. That's only one way. So this is actually 8C3 into 1 into 5 factorial, which is the arrangement of the remaining 5 people. Therefore, what's the process that we have followed? We have chosen 3 places for the CEO, CTO and COO, and we have done all the possible arrangements for these 3 people, right? And then we have arranged in each of these cases, the remaining 5 people can be arranged in 5 factorial ways. Therefore, these 8 people can be arranged in 8C3 into 5 factorial ways, which is equal to 8 into 7 into 6 by 6 into 120. 5 factorial is 120, and that gives you the answer as 6720. Remember, the process followed over here is a 2-step process. The first step is find the number of arrangements of the CEO, CTO and COO, and that is 8C3 into 1, and find the arrangement of the other 5 people, which is 5 factorial, and then you multiply it together, because in each of the 8C3 into 1 ways, you can arrange the other guys in 5 factorial ways. Let's do this question. How many ways can the letters of the word permutation be arranged without changing the order in which the vowels appear? That is, the first vowel E should remain as the first vowel, second vowel should remain as the second vowel in the new arrangement, etc. Alright, pause the video, give it a try, and then let's do it together. Alright, we are back. Let's do it together. Now, the given word is permutation. Now, let's identify the vowels in this word. Alright, so we have E, U, A, I and O. And the given condition is that in any arrangement of these letters that we form, E should be the first occurring vowel, U should be the second occurring vowel, A should be the third occurring vowel, and after that you should have I as the next occurring vowel, and then you should have O. So this order has to be maintained. Alright, now how many letters do we have in this word? We have a total of 11 letters. Alright, now out of these we have seen that 5 are vowels. Now let's take 11 places over here. So that's 3, 4, 5, 6, 7, 8, 9, 10 and 11. Now in how many ways can we choose 5 places out of these 11 places? We can do that in 11C 5 ways, right? So that's choosing 5 places out of these 11 places. Now once we have selected 5 places, within those 5 places, how many ways can we arrange the 5 vowels? We can do that only in one way to maintain the order, right? So what do I mean with that? For example, if I choose this place, this place, this place, this place, and say this place. So that's 5 places. That's one of the 11C5 ways, right? Now, in these 5 places, over here I have to put E, over here I have to put U, this one would be A, this will be I, and this will be O, right? So there's only one way in which I can fill the vowels in these 5 places. That's why I can only arrange these 5 vowels in the 5 places in one way. Alright, now how many places am I left with? So I'm left with 1, 2, 3, 4, 5 and 6 places, right? Now in these 6 places I have to arrange 6 letters. Now you can see that the letter T is occurring 2 times, right? So in how many ways can you arrange 6 letters in 6 places where 2 letters are repeating? You can do that in 6 factorial divided by 2 factorial ways, right? Now over here we have seen that we can choose 5 places in 11C 5 ways. Now in each of these choices we have only one way of arranging the 5 vowels, and the remaining letters can be arranged in 6 factorial by 2 factorial ways. Therefore, the number of arrangements possible is 11C5 into 6 factorial divided by 2 factorial. And that is your answer to the question. Let's do this question. There are 5 boys and 7 girls who study in the same class. Now we need to arrange them in a line such that no 2 boys are sitting together. Alright, pause the video, give it a try, and then we'll do it together. Alright, I hope you have given it a try. Let's do it together. Now over here the arrangement is in a line and it's mentioned that no 2 boys should be sitting together. Alright, and we have 7 girls and we have 5 boys. Let's arrange the 7 girls first. Let's take 7 positions to put the 7 girls in 7 places. Now 7 girls in 7 places can be arranged in 7 factorial ways. We have already seen that n items, if they are to be placed in n positions, it can be done in n factorial ways. Alright, now what are the places in which boys can sit? It's over here, right? Because boys should not sit together, so you should have a girl in between them. Therefore 1, 2, 3, 4, 5, 6, 7, 8. You can place boys in these 8 positions. Alright, and you have 5 boys, right? So boys can sit in 8 places and you have 5 boys. So 5 boys in 8 places can be seated in 8p5 ways, right? What is 8p5? The number of arrangements when you have to select 5 items out of 8 items. So in this case, out of 8 positions, you have to choose 5 positions, and once you have done the selection, you have to arrange the 5 boys in the 5 places. So that can be done in 8p5 ways. Now doing this and this, right, arranging the girls and arranging the boys can be done in 7 factorial into 8p5 ways, and that's the answer to this question over here. What is this? That can be done as 7 factorial into 8 factorial by 3 factorial, right? And you can solve it if the question demands. Let's do the next question. We need to arrange the 5 boys and 7 girls in a line such that all the boys are always together. Alright, now we have 7 girls and all the boys are together, so that can be considered as one unit. So this plus this totals 8 units, and 8 units in 8 places can be arranged in 8 factorial ways. Alright, now in each of these 8 factorial ways, the 5 boys can be arranged in 5 factorial ways. What does that mean? For example, one way would be you have the 7 girls like this: G1, G2, G3 up to G7, and you have the 5 boys as B1, B2, B3 up to B5. Now, the next one in 8 factorial would need this arrangement to be different, right? Now, keeping this arrangement the same, we can just shuffle the boys among themselves in 5 factorial ways, right? So you again have G1, G2, etc. up to G7, but instead of B1 over here, probably you have B2 over here, B1 over here, B3 over here, B4 over here, and B5 over here, right? So keeping the 8 units arrangement constant, we can arrange only the boys in 5 factorial ways. So that can be done for each of the arrangements in the 8 factorial ways, right? Therefore, the answer to this question is 8 factorial into 5 factorial. Let's do the next question. It's mentioned that these 5 boys and 7 girls should be arranged in a circle such that no 2 boys are together. Alright, pause the video, give it a try, and then let's do it together. Alright, we are back. I hope you have given it a try. Let's do it together. Now, no 2 boys are together. Alright, that's the criteria that we need to keep in mind, and it's a circular arrangement. Let's first arrange the 7 girls around a circle. We have 7 girls, and we know that these are not symmetrical bodies. Therefore, around a circle, you can place them in 7 minus 1 factorial ways, which is equal to 6 factorial. Alright, so only arranging the girls around a circle can be done in 6 factorial ways. Alright, now how many positions are there where boys can be placed such that the given criteria is met? You have a total of 7 places. 1, 2, 3, 4, 5, 6, 7. And in these 7 places, you have to position 5 boys. And that can be done in 7p5 ways, right? And it's no longer a circular matter, because once you fix something in a circular arrangement, it becomes equivalent to a linear arrangement. So in each of these 6 factorial ways, the girls are already fixed around the circle. Therefore, in each of these 6 factorial ways, you can arrange the boys in 7 places, and we have 5 boys. So that can be done in 7p5 ways. Therefore, you can arrange the girls and the boys in 6 factorial into 7p5 ways, which is the answer to this question. Let's do the last question over here. We need to arrange the boys and girls in a circle such that all the boys are together. Alright. Over here we have 7 girls and we have 1 unit which is comprised of 5 boys. So we have a total of 8 units, and these 8 units can be arranged around a circle in 8 minus 1 factorial ways, which is equal to 7 factorial. Alright, now in each of these 7 factorial arrangements, this 1 unit can be arranged in 5 factorial ways among themselves, right? Therefore, the answer to this question is 7 factorial into 5 factorial.